Okay, hi there again, my name's Will, and you may be wondering why is a CDN guy talking to you about player optimizations. Actually, the question you should really be asking is why is a player developer working as a chief architect? Because that's actually the reality of my life. I don't have a good answer for that one. I was hired as a player developer at Akamai 10 years ago, and I used to run player engineering there. So a lot of this is based upon those early days, and this is when HTTP streaming was coming about. And today in the architecture role, it's clearly apparent that in the HTTP adaptive streaming world, the player is the kingpin. You can have a great encode, a great distribution, and if a player requests the wrong segment at the wrong time, you ruin the experience. The QoE goes down. Conversely, if the CDN screws up, a good player can compensate for that and keep the experience going. So there's a lot of logic in things that players should and should not be doing, and I'm going to go through 15 subjects that I have gathered. I only have 20 minutes, so I'm at a strong risk of running out of time on this one. I want to start with something called segment abandonment. For you young ones in the room, that's a video clip from Dr. Strangelove, where the villain is riding a nuclear missile down into the ground. And I put it up there because many players ride video segments into the ground. So here's what it looks like. So I've got a timeline, left to right is time, and we're looking at buffer loading. So a player will basically download bits. While it's doing that, don't know if you can see my mouse, I guess not. The player buffer is going to degrade, we load the segment. And this cycle repeats over time, and we get the traditional sawtooth pattern if you look at your player buffer. Then what happens is we download the next segment, but this one's loading slowly. So look at the gradient of that orange line. It's the download rate. The player just doggedly hangs on to this segment. The segment might be 6 seconds long, but your throughput dropped in half. Now it's taking 12 seconds. You only had an 8-second buffer, so you've basically buffer emptied, and your user has a discontinuous experience. So what should happen? So we start off with the same alignment for the player. We have a good segment. We have another good segment following that. We're in our steady state load condition. And now the player should look at this download curve. It should be monitoring the download of its segment while it's happening, and it should decide, it can calculate, in fact, that segment C is not going to be complete by the time my buffer empties. At that point, it should abandon the segment, abandon that load, and switch to an alternate, which in this case I'm calling C-primed. Now, this might be a lower bitrate, or it might be a source, an alternate source coming from another CDN or from a peer if you're doing P2P. Either way, hopefully the throughput at that point improves, and you prevent the player buffer draining all the way down to the line. Now, if you've got a modern player, if you're talking to TheoPlayer, BitMoving, Cast Labs, Demux, Realize, their players are going to do this. But there's an awful lot of players out there today that simply, when they commit to loading a segment, they wait till the end of it, and they ride their buffer down into the ground. So make sure that your player has something similar to this behavior built into it. Now, let's go back to the subject we were addressing before. What about if we look at how does this work in a chunked environment? And a lot of people are talking about 6-second segments and 2 seconds latency, which is a cool demo to show off. But think about the complication. I'm downloading a 6-second segment. Suddenly, it's going to take 10 seconds, and I only have a 2-second buffer. And if my switch point is the start of that segment, there's no way that can possibly work. So there's a little hidden caveat, and I highlighted it in yellow here. If you're doing chunk transfer, your player buffer must be longer than your segment duration. So a practical operating point might be a 3-second buffer with 2-second segments. That would give you 3.5 seconds end-to-end latency, assuming your encoder and your CDN are taking up half a second. And the player has at most 1 second to make this decision. And there's a pretty interesting behavior that happens here. So this is a somewhat confusing chart. Same thing, time going left to right. And the green line is us loading a 2 megabit per second segment with chunked encoding. The light blue line is our decode. We're loading our buffer and we're burning it out at the same time. And if you remember Mark from Twitter in the prior talk, he actually showed this chart happening in his player. The result is your buffer is actually stable. You're downloading the content. In theory, it's stable. You're downloading it at the same rate that you're filling it up. And the pattern looks like this. But let's say we run into a problem. Now we're down, our 2 megabits, it's not downloading at that rate, it's downloading slowly, which is the green line. We're going to start eating into our player buffer now because our decode rate is pretty constant. At that point, we need to abandon. So here the player is switching to a 1 megabit per second. And notice its download rate is steeper. The line is steeper. That's because that segment now in the chunked world is fully available. So its speed is not limited by the encoder. Its speed is limited by the connection rate. So it's going to come faster. And as a result, my player buffer recovers slightly. And then once it catches up with the encode rate again, that download rate will slow, so my buffer will stay steady. And this pattern actually repeats out. I won't go through all the steps. And the player is actually able to recover after switching down and reestablish its target buffer, which in this case was 3 seconds. So a caveat, if your player is doing chunk-based transfer, you need to have a buffer length larger than your segment duration, or at least your switch interval. They may be coincident. Number 3, and this is for the Dash guys in the room. Place your init files in your manifest. Some people do this, some don't, but it's actually very useful in reducing video start time or getting your video to start quicker. So at the top, we see a sequence. We're loading a manifest. We're loading 2 init files, and then we're loading the media segments that follow on those from init files. And notice the one media segment took 255 milliseconds to download. And you may say, well, that's a quarter of a second, so what? But if we want our video to start in 1 second, that's 25% of my delay right there. So down at the bottom, you can see a Dash manifest. You're actually able to encode your init segment as base 64 and place it into your manifest. So yes, your manifest will get larger. It'll get larger by more than I'm showing there. There's an ellipsis in there. It would be several lines, actually, of data. In fact, 1.2 kilobytes of data. But it's still faster to download that larger manifest once with a single operation than it is to go back and make the repeat requests for the init segments. So explore this and at least see what it does. You can shave off 25% of player start time by following that. Another hint, and this applies to both HLS and Dash players that are using ISO-based media segments or CMAF, load your init segments in parallel to your media segment. So by the time you're loading an init segment, you've already committed to that representation or that variant. And again, I've shown it larger here. We're loading a manifest, we're loading 2 init segments, and then you notice the video segment in the waterfall is delayed until the init segment was retrieved. And that is the correct order. You need to put it into the source buffer, but you could, in fact, request the init segments and the media segments in parallel and not waste, again, 255 milliseconds there. So this is another approach. Use parallel requests when you know that the data can be requested concurrently, and you'll decrease your startup time and increase your speed to startup. Number 5, use request headers or query args to send useful information to CDNs. So mostly your player's just sitting there requesting segments every 4 seconds or 6 seconds, but this is a missed opportunity to provide some very useful information. Now, what type of information might we consider useful? At the top of the list, I put session markers. So put yourself in the place of a CDN. Our edge server might be seeing 10,000 requests per minute on the edge server, or 66 million requests per second across our entire surface. There's many playing sessions going on. So we got thousands of log lines per second coming in on that server. And someone asks us, well, did this player rebuffer? The edge server is stateless. It can't tell a segment downloaded from one player from a segment downloaded from somebody else. So by adding in a GUID, so a pseudo-random identifier of some type to your session request, to your segment request, we can tie segments associated with the same session together. And then we can give you back stats saying, your player this user watching this video was likely to have rebuffered because we can see that the segment delivery time exceeded the segment duration. So it's a very useful property, and you can add that to the log. Every CDN will allow you to add that to the logs as well. So if you're extracting logs from the CDN, you can cross-correlate that data with your own playback session data. But if you don't add it to the server logs, we're going to lose that entirely. Another interesting one is segment duration. You might say, well, how does the CDN care about segment duration? Again, our problem is knowing when we're doing a bad job delivering video. If we take 6 seconds to deliver a media segment, were we good or were we bad? So if it was a 10-second segment and we delivered in 6 seconds, we're good. You should always deliver media segments in faster than the time it takes the player to play them back. But if we delivered a 2-second segment in 6 seconds, we're doing really badly. We're causing the player to rebuffer. So by you telling us what the segment duration is and us knowing how long it takes us to generate the segment, we can generate real-time stats on whether we're likely to be causing players to rebuffer. And in fact, at Akamai, we've rolled this out today. We are collecting with every media segment, we're trying to guess what the segment duration is by looking at the frequency interval. But to remove the guesswork, if you tell us what it is, we can give much more accurate stats. Another one is the max bitrate that you require. So say you're playing back video at 2 megabits per second, and you're connected at 30 megabits per second. We are going to burst that segment to you as fast as we can. And that might be great, but the trouble is there's other people, you're not alone on that server. We could have sent you the 2 megabit segment at 10 megabits, 5 times faster than it plays back, and your player would have been just fine. And we could have given another 20 megabits of throughput to somebody else. And that somebody else might be you next time. So by telling us what's the max bitrate you actually need an object at, we can throttle its delivery. And we'll throttle it to a point where your player's still getting good performance. We can be 3 times, 4 times, 5 times its playback rate, but we cannot over-deliver the segment. You don't need a segment in 200 milliseconds just because you're on fiber. So these are just useful properties you can send. Number 6, provide hints to a player as to where to start. So what's your player's startup logic? So there's a lot of people who say, well, you always start at the lowest bitrate. This was common philosophy 6 years ago. It's really a terrible experience. Again, somebody with a 100 megabit per second connection should never watch 640p video for 6 seconds as they start watching something. There's no reason for that. Now, conversely, if you start a user too high, you have that problem where the video starts, runs a few seconds, and you go straight into rebuffer while the player switches down to something more appropriate. That you also want to avoid it. And it's somewhat of a fallacy that always starting at the lowest bitrate improves your video start time and it minimizes it. And it's true that it does, but it does it by a small amount. And the price you pay for that, which is bad quality for several segments, is really not worth the very small gain in video startup time. So what are some better solutions? 1, see if whatever CDN you're using can provide a hint to you. By the time you're requesting media segments, you've already requested other stuff from the CDN. And it could be telling you what the throughput is by means of response headers and give you at least a ballpark guess. Are you a 0 to 2 meg user, or are you a 2 to 10, or are you a 50 meg user? And it can give you a bucket at which you can then make a reasonable start for your video. The one I actually like is run an actual bandwidth test. So again, when you come to a page with video in it, and as that page is building, you can be running in the background a quick little test, download a test object, and have a real-time estimate of what the throughput is between that player and that server at that time. And make sure your test is run to an object that's stored on the media delivery server and not the web page delivery server. They could be 2 entirely different servers. But that's the most accurate. You can also, if your system is getting real-time data from peers on the same network, use that to help new peers joining and guide them as to what their connectivity is likely to be. This is useful for mobile networks. The one that most people do and that I think is reasonably unreliable is they set a cookie for what connectivity the user had at the last playback session. And think about it. You're at home on your 100 megabit cable. So you put a cookie, this very well connected. Then you come here to the conference. You're on shared Wi-Fi. It's going to take that cookie and try to start you at a 4K stream, which you're not going to be able to stream. So if you do use cookies, or you do use IndexedDB or any sort of persistent state storage between sessions, as a cache key, store the network that you're on. So if you know you're in the Hyatt and Wi-Fi, you store one target duration. If you know you're at home in another. And if you don't know what the AS is, because in a JavaScript-based play you don't know that, you need a server-side service that you can call and it'll echo back what your network characteristic is, and you can store that in your cookie. Number 7, never trust the client clock. It's amazing how inaccurate even mobile phones are. We think with GPS that they must be super precise for time. This is a screenshot from my own phone. So if you go to time.is on your browser, it'll tell you what your system clock is. You can try it right now. My phone, AT&T, fancy phone, 1 second out. And you have no way to adjust that. Now, in the Dash world, this is a problem because Dash requires accurate UTC time reference in order to play a live stream, especially a low latency live stream. On the Apple side, HLS, it's clock free, and that's one of the benefits of HLS. You can have a wildly inaccurate clock, and you can still start a stream accurately. But on the Dash side, you need to know the time. So use an external time source is the answer. We provide one. It is not NTP accurate. But it's still more accurate than trusting your local client clock. So if you can, decouple your player entirely from the local clock. And what you do is you calculate the offset. You don't constantly ping some time source, but you calculate what the delta is when you start playback, and then for elapsed time, you can trust the local clock. But for absolute time, you want an external reference. And this solves a lot of problems. In Dash.js project, we had so many issues 5 years ago just using system clock. We switched over to external time source, had far fewer problems. So I mentioned HLS has a clock-free solution, which is great. But the corollary to that is it's an opaque timing model. So if it's deceptively simple, you download a media playlist, you find the last segment in there, or the last 3, and you load those, and off you go. But the trouble is segments might be 6 seconds in duration. So here I come, I download my media playlist, and once I receive it, the segment boundaries there represent my segments. I need to start decoding from the start of them. So I'm going to, across my cohort of clients, I'm going to have clients whose latency or time behind live ranges from 0 seconds to segment duration, which might be 6 seconds. So you always see this variation. Your clients are always distributed 0 to 6, 1 segment duration apart from each other, because they're randomly joining the stream at any time. And the latency they get while they join will be random. Now, they have an option to decode faster than real time. Some players might do this. They might seek forward, essentially, before starting playback. But another solution would be to do a head request, find out where you are, and then probe for a changed media playlist. So you can use any of those properties there to figure out if you've got a new one. And as soon as you get a new one, you know it's fresh, so now you can constrain the latency. Now, we don't like probing too much. We don't want every client making 10 requests. But maybe if you care about keeping your clients at a consistent latency and one that's not distributed by segment duration, then think about what your startup routine is with your HLS players, and don't randomly just request the last segment and start playback. Number 9. Estimating throughput when faced with chunked encoding. So this has been covered several times today. I prepped these slides 2 months ago. I didn't know Ali was going to do a presentation. We've been trying for a long while, machine learning, averaging, side loading of test payloads to get a good solution for chunk-based transfer. And I think this paper, I've already showed these slides actually, is an elegant and simple approach to this problem. So it's really a practical response to say that these chunks are not all identical. So some of them are grouped together and I can trust those for timing. Others are separated and I'll discard them. And I can collect the ones I want and generate an accurate model. I did have questions for Ali about what happens if you request the segment right at the start when none of them have been accumulated and therefore they're all separate. And I think that's, maybe there's some additional logic you have to apply to wait a bit to get sufficient chunks to make good measurements. Yeah, but it's certainly a good step ahead. So if your player is playing back chunk-based transferred content and you want to do multi-bitrate, I highly encourage you to investigate this solution and check it out. As I mentioned, the accuracy, I was quite surprised with what you could do. Now, another subject that's already come up today, which is awesome, catch-up and rate adjustment. So a live player, traditionally, when it starts a live stream, has one chance to determine its latency behind live, and that's when it joins. Because once it's joined a live stream, it's playing out the content at the same rate the encoder's making it. It's playing out 1 second of content every second. The encoder's making 1 second of content every second, so once you start, you're at a fixed position behind live. And the trouble is, once you rebuffer, you fall behind by the accumulated total of the time you spent rebuffering. And before you know it, you've got players all over the spectrum of time behind live. So the useful characteristics, and we started to see it now, is that when you start playing a stream, you can play it slightly faster or slightly slower. If you play it slightly faster, you're going to pull yourself closer to live. If you play it slightly slower, you're going to drop back from live. But the point is you can alter your latency by adjusting your playback rate. Now, Mark from Twitter raised a good point that audio files might notice this catch-up if you do it at 5% or 8%, or even I notice it at 20%. But most people will not. So you can choose the catch-up rate, and it's, in my mind, a very useful tool. So here's a chart. In this case, the player had a 3-second target latency, but when it requested the 6-second segment, it ended up with close to 6 seconds of latency. It was unlucky. So what it did, it accelerated its playback and pulled itself down to that 3-second target. After that, it had a slow segment for delivery. So that raised its latency all the way back to 8 seconds. But again, by accelerating its playback, it pulled itself back to its target. So this is useful for 2 reasons. It allows players to seek and sustain a target without interrupting the playback experience, without the buffer, spinner, and seeking forward. And the side benefit is synchronization. This is a simple, cheap, and very effective way of getting all your players playing the same content at the same time, without the complexity of WebSockets and discovering each other on a network. You simply give them a time source, you tell them to be a certain distance behind latency, and you allow them to adjust their playback rate to reach that target. And you don't have to do it at low latency. You can have all your players at 30 seconds behind live if you want them. So another very useful tool. It is somewhat of an art and a science combined. The art is don't ruin the user experience, and the science is pick the number. And it doesn't have to be the same catch-up rate. When the user starts, you might want a very low one so that they're not sensitive to it. But if there's a small rebuffer, you might want a very quick catch-up rate in the middle of a sports game so that they get back to the experience and they're less sensitive to that alteration. Number 11, similar to this, and I mentioned it earlier, I think, in feedback to a comment, we should get away from the notion that a live player should have just one target buffer. So assuming you train your player to stay 3 seconds behind live, it is not a ground truth that all players in your system should hold that level. They can't, okay? They're going to have a variability in their network, higher RTT, jitter, packet loss. Some of them, the ratio of the throughput of a connection to the bitrate will vary. And also, it's the application target latency. In Europe, there are legal limits on how far you can be behind a live stream if it's gambling or sports betting. So really what I encourage system providers to do is pick a range. So if you look at the new DVB or Dash specs, there's a target latency for a service. There's also a minimum latency and a maximum latency. So you might say, I want you to be 3.5 seconds behind live. You must never be closer than 2 seconds, and you must never be slower than 10 seconds. And then train your player. Let the player use its knowledge of the environment to pick the happy position in that range. Try to get to the target, but if it can't sustain it, don't sit in this endless loop of catching up to live, falling behind, catching up, falling behind, rebuffering, which players do all the time. Allow the player to intelligently look at its history, its short-term history, and then move itself to a place where it doesn't rebuffer. And it has to do this constantly because its network conditions might change. Number 12, variable length range requests for VOD. So both HLS and Dash allow you to describe or to store your content as a contiguous track file, an hour of video. So what a player will do, again, this is a Dash example, it'll load a CDX, which is an index essentially, and then the player uses that to request segments via range request. And what most players do is request one GOP at a time. This GOP might be 2 seconds, 4 seconds, but the player will just sit and request one. And the reality is, you have tremendous flexibility here. You have this index telling you where all these GOPs are. You might start out requesting one at a time, but you could then request 2 or 4 or 10. Remember, this is VOD, so these GOPs are always available. It's not true for live. And why might you want to request larger objects? Well, larger objects might allow your TCP window. If you're HP 1.1, a larger object will allow you to burst more on TCP, and you'll actually get a higher effective throughput than a very small, say, 1 second or 2 second object if you requested a 4 second object. Additionally, for radio performance on mobile devices, if you can request 20 seconds of data and then shut your radio off for 15 seconds and then request another 20 seconds of data, it's much better from a battery point of view than keeping a radio in constant transmit mode and requesting data. So there's some tricks you can do with track files. So track files are an elegant solution for storing VOD. You have one object there instead of 2,000 on the server. That's good. And they also provide a clever way for the player can experiment with retrieving the data. It doesn't have to do it one GOP at a time. Number 13, don't randomly pick target durations that are integer seconds. So ask yourself on your system, are your segments 2 seconds, 4 seconds, 6 seconds in duration, like 6.000 seconds? The reality is these are nice for humans. We like to count in integers, but they're not good for audio and video sample rates. And in fact, what you want is audio and video segments, which are now demuxed in the future world, or in the world we're moving into. You want them to end at precisely the same time. We have many player problems are caused by audio being 0.032 seconds less than the video. And the player sits there, it wants synchronized audio and video, and it's waiting for that missing audio that's never going to come. So the reality is there's a solution space. So if, depending on your video frame rate and your audio sample rate, there's certain intervals. So 30 frames per second, 48 kilohertz AAC audio. If your segment is 4.8 or 1.6 or 6.4 seconds, you will have integer video samples and integer audio samples. Now, this sounds fantastic. What I'm not showing you here is where this doesn't work. So for fractional frame rates, if I show you the solution space for 29.97, I think it's ridiculously high segment duration. So it doesn't always work for that, but at least if you're dealing with these frame rates here and we're dealing with integer video frame rates, then pick a number that's not a human integer, but is something that makes more sense and allows you to precisely align audio and video segments in a demuxed delivery world. Number 14, and I think I'm preaching to the choir at this point, standardize on CMAF containers for both your HLS and your dash. This is a chart. Apple has actually led the way here with this is iOS deployments. As of today, less than 3% of iOS devices worldwide do not support HLS with an ISO-based fragmented MP4 container. That's a very small number. And what you're going to see this year, 2019, is some very large providers making the transition from HLS TS over to an HLS ISO world. And the advantage of that is many. It's reducing the objects you have to store. It's common DRM across all of them. And if you are delivering both HLS and dash at the same time, you can do it from the same media segment. So you get much more increased CDN cache efficiency at the edge. The problem that you might say is, well, what about my encryption problem? I've got my CBCS versus counter problem that's prohibited me from doing that in the past. But what we're seeing is a gradual move, and in fact accelerating this year towards CBCS being the predominant and supported format across all formats. So in anticipation of a world that supports CMAF containers with CBCS encrypted content, think heavily now about, if you're designing any sort of workflow, moving it over to that. And there will be some landmark announcements this year of large companies who are doing this, so you will not be alone. And then my last one, implement multi-CDN in the client versus the server. So multi-CDN is a reality. Most people don't use one CDN, they use 3 or 4. So the question is, which one should your client use? There's many solutions that allocate CDN only at the startup of a video. So they'll pick the best performing CDN at that startup time, and then you're stuck with that for maybe an hour. And that CDN could be terrible in 30 minutes time, but your player is just stuck there loading from it. So server-side solution is not the best. A client-side solution is much better. And in my mind, the optimum is a client which is evaluating with every segment which CDN it should be using. And I think Pierre-Louis from StreamRoot spoke about exactly this yesterday. So let's say we move to that world. The danger is, and what I don't want players doing, is requesting one segment from CDN A, one from CDN B, one from CDN C, and one from D. CDNs, we don't like one object just randomly out of the blue. It's not in cache. We've got to go back to origin. It's going to be poor performance. We also prefetch segments. If you ask us segment 23, we can go and fetch segment 24 in anticipation of you requesting it. So by requesting one object at a time in a multi-CDN client environment, you're actually making your experience worse. So I show there the colored letters is a hypothetical startup. If I got 4 CDNs, A, B, C, D, I'm going to request 4 segments from A, then 4 from B, 4 from C, 4 from D. That gives the CDN to ramp up and gives me a fair comparison. And after doing that, I might then decide B was the best performer. So I'm going to bias my download to B, but I still need to check on the other ones because maybe they're not better than B. So I'm going to download a lot of B and then do some A again, and then a lot of B and do some C, and a lot of B and do some D. And if those other tests give me a new best winner, I'm going to switch over and bias it towards one of the others. I'm not saying this is the absolute way to do it, and this is highly simplified, but stay away from requesting one segment at a time. That's really bad for all CDN performance, not only the one I work for. And I look forward to sophisticated client schemes coming out, and I look forward to client schemes that are actually talking to the CDN and say, you know, are you having performance? Sometimes we know we're going to have bad performance in 30 seconds, and you might want to proactively switch clients away. And could we be telling the clients that? So there's a lot we can do. It's far more sophisticated than what's being done today with multi-CDN delivery. And I ended 45 seconds late, so thank you very much.
Questions? Oh, many. I will go to the last.
So I think doing the header hinting both in and out from the CDNs in regards to hinting to the players and also hinting to the CDNs is super valuable. But one of the ways that is a reality now in the multi-CDN world that we live in is that we need kind of some unification across that from different CDNs. Have you seen that been taking place? Have you guys been initiating that in any way so that the same headers can be used or are being used by all the different CDNs to have this type of hinting control?
Yeah, that's a great question. So every CDN has some different idea. I think this is an excellent candidate for somebody like the SVA, if Jason's listening. Yes, he is. To standardize this, there's no benefit that we don't want proprietary Akamai headers, and we don't want fast. You want your players sending Fastly headers, Akamai headers, Limelight headers. Let's all agree on some useful names and standardize them. The question would be where to do it. And it's not a dash, it's not an HLS. And it's not a W3C initiative. So we need some external body to standardize it, but that's more a process-oriented problem. I think the industry community, which is really coming together for video a lot more now, this should be something we should be addressing. And we don't have to overcomplicate it. A simple set of headers and a one-page definition, and it's far more likely to be implemented widely than buried down in some 100-page doc somewhere. So I will support that, and if anyone's interested in collaborating with us, come and speak to me.
Ali, you had a question?
Yes, so any plans or expectations for Quick?
Yes, so we had a quick talk yesterday.
Yeah.
G-Quick, Akamai deploys G-Quick now. We're the second largest deployment after Google. We've had it for 2.5 years. We're also transitioning over to IETF Quick. Everything that was mentioned yesterday about the complexity and that is true for us. One additional factor we see with Quick is the increased CPU load. So you don't get it for free. There's a higher CPU cost to delivering quick traffic than non-quick traffic. I'm talking HTTPS comparison. And this has been significant for us, and it's the reason we haven't deployed Quick globally for all requests. So today, if you request Quick from Akamai with alt service, we're going to acknowledge just 5% of those and return Quick. That's still millions of hits, and it allows us to do a lot of data testing, but it's not something you can run a service on. So we're doing a lot of work to make sure that Quick can be implemented efficiently. Otherwise, the last thing you want is an increased CDN bill. So we're standing, and that work is being done with IETF Quick. So as Quick comes out of IETF, expect broad support across CDNs, and also expect CDNs to then compete based on how efficiently they can deliver Quick.
I just want to make a note here. A lot of things you mentioned regarding clients sending some useful information back to the CDN edge and that sort of thing. Those are really pretty well studied and specified in Dash Part 5, Server and Network Assisted Dash. And there's also an IOP for that in Dash IF. So I just want to make people aware of it.
Maybe I should read Dash Part 5.
Yeah, maybe you should. Yeah.
Well, the problem is when Dash specifies something, then the Apple community see that as something that's not applicable, or outside. So I worry about stuff. When I mentioned stuff buried inside a 100-page document, I was somewhat referring to that. So we need to externalize it and make sure that it's...
It's not a Dash-specific solution.
It
can be
isn't, but
extended.
it's inside a Dash spec. So maybe there's an issue there. We need to externalize it. Things like SAND do this already. It's communication. But again, that's quite Dash specific. Can we generalize it and make it more useful and therefore more deployable?
Thank you very much.
Thank you.